So there's 3-1, which means things can change a lot, either up or down. So one has to be careful with this. Yes, you do have a cheat sheet on the final. One sheet, you gotta write smaller and smaller and smaller. So that you have a magnifying glass.
How many questions is on it?
It's about the size of 2 tests. It's about 40 questions. Maybe 35 to 40, something like that. You have plenty of time.
Do we have to turn 4 homework assignments with it, or is it just gonna be our normal?
No,
2?
once we're finished with the next test, that's the last homework assignment.
Oh,
In other words, the last section of the course, you don't turn in homework on. That does not mean not to do it. The
Is that
last
homework?
section of the course is algebra.
is that homework?
Is everyone here algebra?
What's that?
Rufino?
When's our final? What day is our final? Like, do we have a date yet?
Does anyone have the spring brochure for the school?
I do, but it's, I left my
Oh,
book.
whatever, it's
No,
in
I
your
left my
car.
books in Castroville.
It's in the trunk of the car. That's where everyone puts it. You got that? Anyone got that? No?
I have this.
It's
How
in there.
come with this?
It's also online.
It's
Oh,
for a
here we
different
go.
class.
Here it is. Here it is, yes, okay.
It's for my English class, but it's like this.
I have it right here, it's little.
Sorry. Okay, yeah, I remember.
Yeah, okay.
There's a little.
It's Monday, June 2nd. Got it?
Thank you.
Okay, this is a school calendar. Spring semester, Monday, June 2nd. Good.
What hour?
Wait a minute, what year is this? 2014.
Okay.
Some of them are like on the 6th.
That's not right, though. We didn't write it correct. All right. It says it ends on June 5th.
Cause I have class on the 6th too for my final, some classes.
When do you have a phone?
I have a final like on the 6th.
On the 6th. This is bad news. No, I mean, it's really bad news, because I have a flight out of here on June 7th.
Me too.
Who else is? We're all just leaving, right?
I was like, wait a second, I
I'm leaving June 9th.
On the 9th? That, according to that, that's the day we have. Yeah, it's as much of a shock to me as it is to you.
But what day is our final?
I'm not sure, I'm gonna have to look. Last time I looked, it was June 7th. But now that one says no.
Well, school's out on Friday the 6th, isn't it?
Well, it says the semester ends on the 5th.
Oh, okay.
Now that's.
That's what this says. It says Friday. See, because I have a Friday class and this is free final. For him.
Yeah, but the question is, when's finals? That's the.
Finals is finals
This
week.
week is this.
I have all my other finals that week too. I have other finals that week, like on Monday I have a final.
What's the date? I'm not sure.
Monday, the June 2nd.
Okay, all right, so she said she has a final on June 2nd, that means ours is on June 2nd. Okay, we're in what's called prime time. Prime time always gets to choose first. So we're gonna do them on Mondays. Monday, June 2nd will be our final. There's your answer.
June 2nd?
June 2nd.
Sure.
So what, your calendar is not, it's not saying,
Yeah,
yeah, it ends on the 5th, but that includes finals.
Yeah, okay.
Yeah.
Is that at the same time?
No. This one will be, this one will be,
I was like.
I think it'll start at 1 to 3. 1 to 3, I think, I'll check out, but usually it does. Usually 1 to 3. Yeah.
How does that work with support services as far as taking the test over the Monday?
Okay, hang on just a second.
How does that work as far as making an appointment to take the test on the 2nd?
On the 2nd?
Yeah, for support services.
Just go there and say, no, sign here for finals. Yeah, and you can get a double time on it, which would take us 4 hours.
Okay, thank you.
Yeah, that's it.
I have another class that starts their final at, oh, never mind, they start at 3:30. So you guys,
Technically, if we stick to the schedule, there won't be any duplication, overlap, or anything like that. But there's some teachers who schedule their classes at the wrong time, at a not allowed time, and that can cause problems. But we're sticking to the schedule, so that's the way it is. Okay, there's that. We're in section 94. We're doing mean, median, and mode, which are ways of determining the center of a statistical group of numbers or raw data. So this is 9.4. Let's see if you have questions on homework.
The 51.
61? 51? Okay. It says compute the GPA for the following grades. And they give you a little table here, which we're just going to actually extend. Put another column in the table. This is the course grade. Now this is the letter grade, which remember we don't have pluses and minuses, but some places do. Credit hours. This is the weighting that the school puts on a particular course. And then we're going to do something called the product. Product of grade times credit hours. Okay, and there's 4 courses. Okay, so we've got general psychology, algebra 1, student success, which means how to study, and English. And the grades were B plus, A, and B. What a great student. Now, you can't calculate anything with letters. The Romans tried to do that for a long time, didn't work. Yeah, Roman numerals, have you seen them? They're all letters. Try multiplying them. What's an X times a C, right? There's a problem there, right? So the question is, how did they build such beautiful buildings without mathematics? They had to have some math. Probably imported it from someplace else. You know, they owned the world at that time, so they could get people from anywhere. All right, but we can't do that. So we have to put in the number which corresponds to that letter, which is up above there on page 563 at the top. A B plus is a 3.5. This is a 4.0 system. The 4.0 is an A, and the B is a 3. Okay, so we need those number grades in order to actually do a calculation. Now, the credit hours are determined by the school. The psychology is a 3-hour course. The algebra is a 4-hour course, well deserved. 1 hour for student success and 3 for English. So the first thing we want to do is multiply the grade that was received in the course times the weighting. So since psychology is weighted 3, it's considered to be 3 times as hard as student success. Algebra is considered to be 4 times as hard. Or translate that into you have to put that much more time in to get a good grade, and they realize that. All right, so 3 times 3.5, that's going to be 9, 10.5. 4 times 4, 16. 4 times 1, 4. 3 times 3, 9. So you total all that stuff up, and you get 26 and 4 is 30, 39. 39.5. Now this is the product of the grade times the credit hours and totals. That's the total of all that. And then what you do is you go back here and determine the number of credit hours by simply adding up again. This is 3 plus 4 is 7, 8, and 3 is 11. And the way you determine the actual GPA is to take the ratio of those two. Grade point average is going to be a ratio of 39.5 and divided by 11. And that will be the GPA for the particular semester. And this is how the school does yours. So this is a 3.59. That's a very good GPA. Considering 4 is perfect, that's very good. Okay, see how it goes? This is called a weighted mean, by the way. In other words, these numbers, this is weighted by the factor of 3, meaning you're not going to put a 3.5 down, you're going to put a 10.5 down, 3 times as much. 4 times that 4, 16, and so forth. So it's weighted by that factor. Okay, any others in the homework? All right, let's go on to probability. We're just going to do very basic stuff here. We'll get some definitions going and so forth. Probability is a different field of math. It's not actually statistics, even though it does have some things in common with statistics. If you take a stat course here, you'll get some probability in it. But probability's basic idea is to learn how to count. And everyone says, oh, I can count. I'll take probability. Well, this is counting like you've never seen it before. Probability is not always easy to count. Of course, the stuff we'll be doing is very easy to count. All right, some definitions. First of all, what is a probability? We all have some feeling for the word probability, but let's get it down in a more mathematical way. Probability of an event measures the likelihood of the event to occur. And that's a rather general idea. Of course, we have to give it some mathematical formula in order to get it into our problems. They give you a couple examples here. And because of these examples, I want to point out something about probability that most books do not, and most people don't realize it either. The probability of picking the winning 6-number combination for the New York Lotto Grand Prize is 1 over 45,057,474. All right, most people will say, oh, that means it's very small. I'm not even going to bother, right? What that means is if you're talking about millions of people who live in New York State, then the probability of getting that winning ticket is that much, okay? You have to talk about a huge number of people or things that are going on before probability even begins to be intelligent, all right? Now, genetic DNA analysis can be used to determine the risk that a child will be born with cystic fibrosis. If both parents test positive, the probability is 25% that a child will be born with cystic fibrosis. Unfortunately, doctors take that and tell it to mothers and fathers. It doesn't apply to an individual. It only applies to millions of individuals. Okay? And this, you should know this, because at some time in your life, you may find yourself in a doctor's office with a diagnosis and, you know, probability of surviving this operation is, you know, and that's, they'll be a little kinder. Depends upon their bedside manner. They actually have courses in their medical schools to develop bedside manner, and obviously a lot of them have flunked. So,
You know,
You're
but
gonna
the
die,
point is,
that's it.
what they're doing is abusing mathematics, okay? They're interpreting it in a way it was never meant to be done. Yeah, so, I mean, the probability of surviving an operation depends on many, many things, some of which can be statistically analyzed and some of which cannot, such as your attitude. But you go into an office and you're told, well, you have 13% probability of survival, and you don't use your attitude well, then you go into depression, right? So this is an abuse of mathematics, and it happens all the time, unfortunately. I just want you to understand that. It only applies to huge numbers. So let's keep that in mind as we go. All right, more definitions. This one is called an experiment. Now these words, watch out because we think we know what these words mean. They mean different things in probability. An experiment is an activity with an observable outcome. All right, for example, coin toss, or rolling dice. All right, you can see an outcome. You've got two dice, throw them over onto the table, and you see what happens. You get one with a 1 dot on it, one with 3 dots on it. Okay, you can see it. There it is. That's an observable outcome. The next definition is called sample space. This is the jargon of probability. Okay, the set of all possible outcomes of an experiment. For example, let's do the coin toss. Well, what could happen if you toss a coin?
Two things.
Head and tails, right?
One can fall on its side. That's the third.
Have you ever seen that happen? Louis, has that ever happened to you?
Nope.
No? It's happened to me. And I tossed the coin and right on its edge. That's very rare. But there technically are 3 outcomes. It's just that one of them is extremely rare, so they ignore it. And they say there's only 2 outcomes. So that would be indicated with an H for the head and a T for the tail. Now, of course, you can't do that. It's too simple. Mathematics wants to have fancy stuff. So what they do is they use set theory notation, which is curly braces. Do not use parentheses. Do not use square brackets. Use curly braces. And they take the 2 observable outcomes, which is head or tail, and separate them with a comma. That is called the sample space for the coin toss. Okay? It simply lists the observable outcomes. Rolling dice, what would you get? Well, they should take 1 die.
Get 1 through 6.
1 through 6, exactly. There's the sample space for rolling 1 die. Okay? All right, now we can talk about the probability of an event with the mathematical formula. That's the general definition. Here's the mathematical formula. It's usually indicated with a capital P, and it's a fraction. The number of elements in an event divided by the number of elements in the sample space Okay, we're through with the jargon, thank goodness, that's it. Okay, so, I'll give you some examples. Find the probability of rolling a 5 or greater on a die. Well, here's the sample space. This is the only thing that can happen when you roll 1 die. You get 1 through 6, okay? You want to get 5 or greater. Well, the only way that can happen is if you get a 5 or a 6, okay? Anything else would be smaller than 5, right? Okay, so what's the number of elements in the event of getting a 5 or greater? 2. Now, the number of elements on there, you're right, you can do the probability. The number of elements for the event itself would be 2. The number of elements in the total sample space? 6. So therefore, reducing that, the probability of rolling a 5 or greater is 1/3. Now, that's expressing probability as a fraction, which it often is in textbooks. But you can express probability in terms of a decimal. You can express probability also in terms of percent. Why? Because you can convert between fractions and decimals and percents, huh? You remember what 1/3 is? It's a repeater, right?
Yeah.
A decimal? Yeah. It's 0.333 dot, dot, dot. In math, we would call that 0.3 with a bar on it, but nowhere else. Don't dare do it outside the classroom. Don't pass out if you do that. Okay. And then if we want a percent, what we do is we multiply this by 100 and attach a percent sign. Well, multiplying it by 100 simply puts it over here, right? 2 over, moves it 2 to the right, so it becomes 33. And then you have this 0.33333 thing, which is also 1/3. It's actually equal to the fraction 1/3. So this is 33⅓%. That's the probability of getting 5 or greater when you toss a die. Okay, find the probability of flipping a coin and having it land on its head. All right, the coin flip is heads or tails. That's the sample space right there. We're talking about a head, so a head would just be that one there. And therefore, the probability of the coin toss would be the number of elements in the event, which is the head, is only one element, and divided by the number of elements in the sample space 2, which is 0.5 is a decimal, or multiplying by 100, that's 50%. Now again, remember this applies to a lot of tries, you know? If you toss a coin the first time, and you want the probability of getting a head, you might find it comes up tails. That means 0. You didn't get a head, right? All right, let's say you do it 3 times. All right, you might get, let's say, 2 heads and a tail. Well, that would be 2/3. But you see, that's not 50%. You've got to do it, what, 50 times? 100 times? And then the probability will start coming out being 50%. Okay? If you do small numbers of experiments, you're not going to get the 50%. That's why I say it only applies to large numbers of things. So when doctors use it in that way, they're really doing a disservice to everybody, including mathematicians. On page 565, it says a class has 4 freshmen, 12 sophomores, and 6 juniors. If one individual is selected at random from the class, find the probability of selecting sophomore, junior, senior. All right, let's see what happens with that. You even get a nice little picture there. 4 freshmen, and they show an icon which certainly looks like a freshman. That's a joke. Okay. 12 sophomores. Only in math do we have to tell people when we're doing jokes. Must be something wrong with our jokes. Okay. All right, you're drawing someone out of a class, huh? And there's how many people in the class? Well, here you go. 4 and 12 is 16, and 6 is 22 people. So the sample space would be 22 people, huh? The number of elements in the sample space in other words, all possible events is 22. But we're asked about freshmen. Okay, well, there's 4 freshmen in there. If we had an experiment where we drew a freshman out of the class, we're drawing from 4 people. So we would form the probability T by putting the number of elements in the sample space, 4, and divided by the number of elements in the number of elements in the event, rather, which is 4, divided by the number of elements in the sample space, 22. And then we reduce it. Both things can be divided by 2. It's 2/11ths. You can convert that into a decimal if you want. And 11ths also are repeaters, aren't they? Yep, a lot of decimals. are repeaters. And this is 0.18, and that's the part that repeats, 1/8. So if you wanted to convert this into percent, you multiply by 100 to get 18, and the next number is a 1. So probably you just drop it and write this as approximately equal to 18%. Okay, what's the probability of getting a junior? Well, for a junior, it's the number of elements in the event, and the event would have 6 for a junior. And that would be, this is probability for a junior, this is probability for a freshman. And that would give you, again, dividing, that's going to give you a 3 over 11. And that gives you 0.27, which is approximately 27%. And then they ask you a trick question. They say, all right, so what's the probability of getting a senior? Well, the event of getting a senior there is, sorry, there's no seniors. So the probability of a senior is 0 over 22, which is 0, which is 0%. So 0% means it's impossible. A probability of 0% means it's impossible. Probability of 1, by the way, means it's absolutely certain. Okay? In other words, if there's one freshman in the class, what's the probability of getting a freshman? 1. Yeah. 1 divided by 1, which is 1. So probability ranges between 0 and 1. In other words, it's a fraction that is somewhere between 0 and 1. Probability can never be greater than 1, because that wouldn't make any sense. Greater than 100% probability? No. That would. You watch the news broadcast, they give you the probability of rain tomorrow, you know? Well, there's a 70% chance of rain tomorrow. They're talking about probability there. Now, they have to talk about probability because the way they measure, you know, the machinery that they use to measure the probability of rain puts in data from tens of thousands of places. You know, that humidity, wind speed, satellite photos, all this kind of stuff comes into them saying it's 70% probability of rain. So there's a lot of data, and therefore the probabilities are pretty good. They're not bad these days at predicting weather. And that all came with computers. Okay. Let's do a little bit more here. Now, these sample spaces are well determined when you talk about die or coin toss. But sometimes the sample space is determined by actual counting of data, raw data. As an example of that, it's on page 566. A dental hygienist records the number of times a day her patients say that they brush their teeth. Now, of course, they could be lying. You never know. But anyway, it's a table. And the table is a very simple one. So 2 columns. This is the number of times a day. And this is the frequency of that response. 1, 2, 3, and more than 3. And 6 people said 1 time a day, 10 people said twice a day, 4 3 times, and 1 said more than 3 times. Now that's obsessive compulsive disorder right there. Brush your teeth more than 3 times a day. I mean, really, get a life. All right. So the question is, how do we do the definition of probability now? Remember, it's that ratio of number of elements in the sample. Okay. Okay, so let's look at this. We've got 6 people saying 1, 10 saying 2, 4 saying 3, 1 more than 3. Okay, so the total sample space includes all the people that were questioned. And that would be 16, and 4 is 20, 21 people were questioned. So this would be the sample space. And the number of elements in the sample space is those people. So that would be your denominator in your probability. So they ask the obvious question. They say, okay, what is the probability of selecting a patient who brushes only 1 time a day? So you take the frequency of that, and that's 6. That goes in the numerator. That's the particular event you're looking at, the 1 time a day people. And the sample space has a size of 21. Again, reducing, 3 goes into that twice, and 3 goes into that 7 times. And guess what? 7 is another repeater. I don't know why they're choosing problems like that, but there it is. So 2 divided by 7. Well, remember 7 is a long, 0.2857114. That entire thing repeats. Okay, so let's just put that in percent notation. That's going to have to go to about 29%. Say that they brush once a day. Okay, the next question is, now this is interesting. What is the probability of selecting a patient who brushes more than once a day? Okay, now how do we figure that out? Well, that would exclude everybody here because they brush once a day. But 2 times a day? Yeah, that works. 3 times a day? Yep. More than 3? Yep. So in order to get the number of elements in that particular experiment, the more than once a day people, you have to go 10 plus 4, 14, plus 1 is 15. So that probability would be 15 over 21, which again, reducing gives you a 3 goes into that 5 times, and the 3 goes into that 7 times. 5 seconds. And you can figure out the percentage for that too. But the point they're making here is that if you take these 2 probabilities and add them together, what do you get? Now those are fractions with the same denominator. So we just add the 2 numerators, right? Which is 7 over 7, which is 1. In other words, when you add together the probability of an event happening and the probability of the event not happening, that has to be 1. Okay? Because either it happens or it doesn't happen. Those 2 probabilities are called complementary. And we use that to calculate some strange little things. I'll give you some examples. The best thing is just go to an example here. It says, if the probability that a washing machine will break before the end of the warranty period is 0.0042, what is the probability that a washing machine will not break before the end of the warranty period? Well, those are called complementary because either one of those 2 things happens. There's nothing else. Okay? So therefore, you know that if you take that 1, which is, total probability, one of these 2 has to happen, and subtract the 0.0042, which is the probability that it will not break, that it will break, then you subtract these 2, you get something like this, 0.9958. So, again, multiplying by 100 and so forth, this becomes 99.58% probability that it will not break. In warranty. Now, all of this kind of a calculation is done for virtually everything that's manufactured and that we buy to use cars They know all the probabilities that your Toyota is going to have an engine failure in the first 5 years. It's very low, but it's there, you know? And so, of course, the better companies sell products that have a very high probability of not breaking in the warranty period. What always fascinates me is, but get just a little bit out of the warranty period, and all of a sudden, everything crashes, you know? I learned a long time ago, yeah, sure, buy a used car, but if it's more than 3 years old, be sure to buy insurance with it, you know? Because 3 years is the manufacturer's warranty on most cars. And if it's older than 3 years old, especially that 3 to 4 years old, yep, that's when things break, you know? Third-party stuff, they buy, you know, radios and air conditioners from other people. And unless they really check out those people and make sure that those devices have a high probability of not breaking, in that 3 to 4 year period, they do. And you know, you can't blame Toyota or Honda or people like that. It's someone else who's manufacturing that. And you know what happened a few years ago with the brakes on the Toyota. You remember that thing? The recall? Huge numbers of cars. Remember that? It was all because of a third-party part, which, by the way, was made in the United States. So here we are complaining about it, the government's suing Toyota and all that. We made it. Isn't that interesting? No, it's not. All right, so there's complementary probabilities. Let's see if there's another thing we should do here. Yeah, let's do one more. It's on page 569 in the homework section. It says a survey was made of 60 participants asking if they drive an American-made, a Japanese car, or a car manufactured in another foreign country. The table gives the results, and it looks like this. Just 2 columns, as always. Country of origin, right here, and this is frequency. And you only have 3 things to choose from: American, Japanese, and so forth, and other. And it turns out in this particular survey of 60 participants, 21 American, 30 Japanese, 9 other. Which is a hard thing to get, by the way, because, you know, a lot of the Japanese manufacturers do actually build a car here in the United States. Honda does that, for example. They've got several factories in the United States. So is it American or not? You know, where do you put it? All right, questions they ask are this. What is the probability that randomly selected cars manufactured in America? Okay, so let's figure out the sample space again. 21 plus 30 is 51, and 9 is 60. So there are 60 people who answered the survey. This is the size of the sample space. Now the event we're talking about is made in America. So that has a size of 21. So the probability, we'll call it probability that's American, 21 divided by 60. And when you divide all that out, it comes out to be 0.35, which is 35%. A little over a third of the people who responded said they had American-made cars. What percent of cars is manufactured in some country other than Japan? Okay, so there was percent probability. What percent of cars is manufactured in some country other than Japan? That would be, I'll call it PO for other. Well, the other includes both this other down here, maybe European, something like that, but it also includes American, because that's other than Japanese too. So in order to figure that out, you'd have to add the 21 to the 9 to get 30, put it over 60, and that gives you 0.5, which is 50% of the cars were manufactured in some other place, not Japan. So it's a very simple idea. That's as much as we're going to do with it. just to give you some sense of how it can get quite complicated, we have the sample space for one die over there. All right, let's say you're rolling 2 dice. What does the sample space look like? Well, it's much bigger, huh? Yeah, because you could get all sorts of pairs, all sorts of combinations. You get a much bigger table of sample space at that point, and it's a 2-dimensional table. And you know, if you want to then talk about what's the probability of coming up with 2 5s, that counting is very tricky. You actually have to count in that 2-dimensional table in a certain way to figure out what the event elements are and put that over the sample space elements and so forth. So while probability looks like a very simple idea, the specific problem can get much more complicated. In other words, what I'm saying is you have to really like this stuff to go into it, because most people just say, where's the math? Get me back to my equations. Okay, let's do some homework. This is 9.5.
Is that 18?
This is 19. And number 37 is going to be especially good for you. It's about a teacher noted the times in which the student entered the classroom. 10 minutes early, 0, I'm sure. No. So, what about your probability? You're rolling for